Hello everyone, welcome to lesson 1.5. Today we're going to be looking at measuring and constructing angles. Oh, and I did forget to put the page number in the corner. So we will be starting on page 38. So if you're following along with us in the book, then that is where you're going to want to turn to, page 38. So in lesson 1.4, and I guess also in 1.3 and 1.2, we've dealt a lot with things being in the coordinate plane, right? We just got done learning about how we can find the perimeter of a shape that is just plotted in the coordinate plane. Remember, we used the distance formula to do that, and then if we talked about finding the area, we used whatever area formula was appropriate, and we found the area and perimeter of different shapes when we were dealing with, again, the coordinate plane, those x and y axes. Now, in lesson 1.5, we're going to take a little bit of a break from the coordinate plane, and we're going to look at measuring and a little bit of constructing, but we're going to look at angles and how angles are formed, how we can find the different measures of different angles when we have not all the information and things like that. So our learning targets, there's quite a few of them, but they're not as complex or as heavy as it looks. Students will be able to name angles and classify them as acute, obtuse, right, or straight. So a little bit of vocab with those words of being able to name and classify angles. Students will be able to use algebra to solve equations to find angle measures. So we'll see things where we have angles like this, and we're given an equation for what this angle equals and this angle equals, and we'll have to add those together to try to find out what this whole thing equals. So that was not an awesome explanation, but that's a quick overview. That'll totally make sense in like 20 minutes when we're done with this lesson. Students will be able to use angle addition to find angle measures. Well, that's what I just talked about right here in this not so great diagram, but we'll be able to clear that up here soon. Students will be able to draw and explain an angle bisector. So this lesson was titled Measuring and Constructing Angles. Since we are virtual, we won't do too much with drawing or constructing angles. We're going to talk about a little bit with how we measure angles, like physically measure angles, but since we're virtual, we won't mess with it too much. If we do ever get back in person, then we might spend a day on constructions and take a look at those, but that's not going to be today. Students will be able to use algebra to solve problems involving angle bisectors, so a little bit of application there. So first we're going to start out with some terms. An angle is a set of points consisting of two different rays that have the same endpoint called the vertex. The rays are the sides of the angle. So a couple of things that might seem pretty obvious, but we had all those terms in 1.1, and now we're putting them to a specific application and building off those for a new definition. So you can see here we have a ray, and technically this would be ray AC. We also have a ray right here, and this would be ray AB. And by our definition, we have two rays put together, and they share this point right here, and we call that the vertex. And the rays obviously make up the sides of that angle. Now, one thing I do want to go over is how we name this angle. So we have a couple different ways. We could call this angle CAB, CAB. We could call it angle BAC, BAC. We could not, so bad. Don't do this. We could not call it A, B, C, or anything starting with A, because A is our middle point, so when we name it, A has to be the middle letter there. So these are bad. We could not start with A. Now I say that, the only time we could start with A is if we just call this angle A. So I guess I say that last thing a little bit tongue in cheek, because we can technically call this angle just angle A, and that is talking about this angle here. Could be angle A, that's one way, BAC, or CAB. So 3 ways that we are able to name this angle. A little bit more vocab. The region that contains all the points between the sides of the angle is the interior of the angle. So we talked about how these are called the sides, and the region that contains the sides, I should not color over that. The region that contains the sides is called the interior. The region that contains all the points outside of the angle is the exterior. So obviously out here is the exterior. Notice that the interior doesn't stop right here. So the interior is not just like this, because technically these lines with this arrow, since it's a ray, these lines keep going and going and going and going and going and going. So the interior would be all this space out here as well. Now let's take a look at the protractor postulate. Now we are at the top of page 39. Consider OB in point A, which is on the side of OB. The rays here that are formed can match 1-to-1 with real numbers from 0 to 180, okay? So pretty much we have this angle, AOB. The measure, keyword, the measure of AOB, the measure of this angle right here, is equal to the absolute value of the difference between the real numbers matched with angle, with ray OA and with ray OB on the protractor. So pretty much what all that is trying to get at is that if we want to find the measure of this angle, which represents this right here, the degrees of that, we could, if we were in person, or if you have one at home, you can line the vertex up with the center of your protractor, line those lines up, all right, and we can see that this line goes through 180, this line goes through 40, so the measure of this angle would be 180 minus 40, so the measure would be 140 degrees. And it talks about the absolute value there because we can't have a negative angle. That doesn't exist. So if you set it up, 40 minus 180 and got negative 140, we would have the absolute value of that. So the degrees would still be 140, and don't forget our little degree sign. Okay? Again, we're not going to mess with a protractor too much, so don't worry about it all that much. But the big thing is we can't be tricked and seeing this and thinking, oh, it's where it crosses the 40, so this must be 40 degrees. Nope, we need to be a little bit more aware than that. It would be 180 minus 40, and that is the protractor postulate. Oh, this is a typo. If you didn't notice, I used a template of all these slides, and that is left from the template. So this should say something like more vocab. So we have a couple more vocab terms that we need to look at. The first one, an acute angle. An acute angle is any angle that measures greater than 0 degrees and less than 90 degrees. So if we're looking at our protractor up here, an acute angle, 90 degrees is here, and it has to be less than 90. So anything that is less than 90. So this would be an acute angle. here would be an acute angle, an acute angle, acute angle, anything. 90's right here, so any angle that's formed that is less than 90 degrees, and just here is one example of that. A right angle, like it says, is exactly 90 degrees. Notice that it has the little 90-degree mark on there, so that's a dead giveaway that we're working with a right angle. Sometimes in some problems, they will show this right angle, and they'll say, you know, find the measure of something. They might have a line that comes out and bisects, and they'll say find the measure of this whole thing, or find the measure of just this side. Well, no matter what, they need you to know that that little line means 90 degrees. So we have to watch out for that and keep that in mind. An obtuse angle measures greater than 90 and less than 180 degrees. So if we have one ray, 90 degrees is here, obtuse angle could be anything that is this way. Now, like it says, it can't be more than 180. So it's anything that's in this kind of section, greater than 90 but less than 180. A straight angle, exactly 180 degrees. So like it has on there, any of our lines, line segments, anything like that are always straight angles, because this is 180 degrees. And again, just like with right angles, they'll point to the fact in some problems that you need to know that a straight angle is 180 degrees. So they'll give you some information, say this is a straight angle, here's some other things, but they don't flat out say a straight angle. Remember, a straight angle equals 180 degrees. That's just something they expect you to know. One way to remember the difference between acute and obtuse, they're kind of easy to mix up. An acute angle, just remember, it's a little cutie. It's real cute and small. An obtuse angle, man, that thing is huge. Massive obtuse angle. So that's the way I remember. Acute little angle is something less than 90, it's acute. And an obtuse angle, you don't want to mess with an obtuse angle because those things are huge, because it is greater than 90 degrees, but still less than 180. So maybe huge wouldn't be the right word. It's pretty big. If you're following with me in the textbook, now we're going to move ahead to page 41, and we'll look at postulate 1.4, the angle addition postulate. Now this is something that we are familiar with, kind of. We're familiar with the segment addition postulate, which remember said that if we have a couple segments, say this one is 10 and this one is 9, that we're allowed to take 10 plus 9, and that will give us this whole thing if it's called A and B. So that's the segment addition postulate, and we are very familiar with that. Angle addition postulate, as you guessed, is very similar. It's saying that if we have this angle and we split it in half, and we can see that it's split in half because of these markers. Just like with our segment, we had the tick marks. Here we have these kind of loops. I'm not sure what the technical name for that is. But it's saying that if we know that these are the same and this is 40 degrees, then we know that this is also 40 degrees. Or on the other hand, kind of on the other side of that, if they tell you this whole thing is 80 degrees, and they tell you that these two are the same, then you can assume that this is 40 and this is 40. Okay? So, kind of two different sides of the same coin that the angle addition postulate does for us. Very similar, again, to the segment addition postulate, but just applying it to angles. One thing that I do want to point out here is that we talked about this word last week sometime. But if these two angles have the same measure, say they are both 40 degrees, then we would say that these two angles are congruent. These two angles are congruent. And the way that we would write that is we would say that the measure of angle, like it has here, that's what that little m means, the measure. So you could put it on there if you wanted to, but you don't have to. You could just say angle RST is congruent. Use that equal sign with a squiggly line over it. Oops, not RST, my fault. Angle RSP is congruent to angle PST. To angle PST. So when two angles are the same, we don't say that they're equal. I mean, congruent, equal really mean the same thing, but in geometry, we like the word congruent. So we say that those two angles are congruent. This is how we would put that in a math sentence. Use the angle sign, name our angle is congruent to, with our equal sign and the squiggly line over top, angle PST. Now here's how we would apply the angle addition postulate. Given that, and this is a problem you'll see very similar to this on your homework, given that the measure of angle LKN is 45 degrees, so LKN, so this whole thing is 145 degrees. They want us to find LKM, should switch colors. Find LKM and find MKN. So we need to find these two things. Now there is not any little loop there on the side to tell us that these two are congruent. So we cannot assume they're congruent. I mean, if we look at them, we can see pretty quickly they're not congruent. So what we need to do is we know that the whole thing has to equal 145 degrees. That this angle plus this angle has to equal 145. So what we can do, and this is a little bit similar to what we've done with our segments when we tried to find the total length of a segment, is we can take this and this and add them together, and we know that they have to equal 145. So really what we're doing here is, I mean, this is a more advanced way of doing something like, say I told you that this was 45 and this was 100. Well, you would just add these two things together to get 145. Instead of just giving you plain numbers, I'm giving you this expression and this expression and saying, hey, these two expressions put together equals 145. So all we're doing is adding each expression together. The first step is we're going to want to simplify with our x's. So we have a 2x and a 4x. That will give us a 6x plus 10 minus 3. 6x equals 138. And that means that x should equal 23. Now we're not done, right? Because we just found what x equals. So if we want to find the measure of angle LKM, this would be 2 times 23 plus 10. 2 times 23 would give me 46 plus 10 would give me 56. I'm going to write x equals 23 up there so I don't forget. Now if we want to find the measure, measure of angle MKN, 4 times 23 minus 3. 4 times 23 would give me 92. minus 3 is 89. So then we know that the measure of angle MKN is 89, and we can't forget our little degrees sign up there. So again, this is something that we are kind of used to seeing, that we've seen before. I guess earlier with the segments, we've taken these and set them equal to each other. We haven't added them together, but it's kind of a similar idea that we're dealing with. Last concept here. Yep. Bisecting angles. An angle bisector is a ray that divides an angle. Okay, so let's stop right there. An angle bisector is a ray, so we know what a ray is, endpoint, and keeps going in one direction, that divides an angle into two angles that are congruent. Remember, congruent means the same or equal. In the figure, YW bisects X, Y, Z. So that means that this is the same as this side. You can use a compass and straight edge to bisect an angle. That's part of constructions, and we won't mess with that too much. Now, this is probably the toughest part of the lesson for me, because I am remembering back to when we had segments, when we talked about segment bisectors, and in the Edpuzzle, when we talked about segment bisectors, I said all segment bisectors have to go through the middle of a segment. So the point I was trying to make is we could have a segment bisector over here, or we could have a segment bisector over here. I did a little bit of research, and the definition, the formal definition of bisect, just means to cut something in half. So the real definition, if I have, oh, that's not a good example. If I have a piece of wood, and I told someone I bisected this piece of wood, that could mean that I cut it anywhere. But, however, the geometric definition of bisect means to split something in half. So, for any of you on that Edpuzzle that got that one wrong when I said true or false, a segment bisector always goes in the middle of a segment, and the answer was false on the Edpuzzle, I was incorrect. A segment bisector, just like an angle bisector, always cuts through the middle of our angle, or last week it cut through the middle of our segment. So I was wrong about that. When we think bisecting, we should think middle, or cutting through the middle. So here's a problem that includes segment bisectors that you'll see one very similar to on your homework. QS bisects angle PQR. So one thing, if on your homework I see these problems and I don't see drawings for them, that's going to look pretty suspicious, because there's no way that you'll be able to do these without drawing them out. So QS bisects PQ. Remember that middle has to be our vertex, R. And QS bisects it. So QS splits it right in half. And the measure of, I don't want to switch colors, and the measure of PQ, oops, I should have labeled this S. PQS is 24 degrees. Find PQR. So find the whole thing. Well, like I said, PQS bisects PQR, the whole thing, and if this equals 24 by definition of a bisector, this also has to equal 24, because that bisecting ray split it right in the middle. So if we need to find the measure of the whole thing, the measure of PQR is 24 plus 24, so it would be 48 degrees. Now, not all of them will be quite that simple when we deal with bisecting angles, but that is a baseline in one simple example of how you will see questions framed that deal with bisecting these angles. So if we look at our learning targets, Students will be able to name angles and classify them as acute. Remember, it's acute, so that means it's a small angle. It's less than 90. Obtuse. Obtuse is huge, so we don't want to mess with it. It's more than 90, but it's less than 180. A right angle, which remember has that little, those two little lines put together right here to show that it's a right angle, or straight. Sometimes with a straight angle, you will see that it has this half circle around it, and that just is telling you and confirming that it's a straight angle, or it'll tell you in the directions. Students will be able to use algebra to solve equations to find angle measures. Well, that's what we did somewhere. No. Yes, that's what we did here, is we used algebra to add this side and this side together. Remember, we knew they equaled 145. We found out what x had to equal, and then we plugged our x back into each side so we could find each angle. So we nailed it. Students will be able to use angle addition to find angle measures. Well, if I would have asked for LKN, then you could have used angle addition. You could have just done 56 plus 89. Here we did use angle addition. We added 24 and 24 to get our nice 48. Nailed it. Students will be able to draw and explain an angle bisector. So when it says draw an angle bisector, it means with like a compass and a protractor. We didn't get into that today because we're not doing constructions today, but I think you can explain that an angle bisector goes right down the middle of, of an angle. Splits it right in half, right? Because bisect in geometry, we're talking about half there. So we're good. Students will be able to use algebra to solve problems involving angle bisectors. That would be like this problem. Again, this was a very simple one, and we won't see all of them to be this simple, but you can imagine how they would throw something that looks like this with these expressions in there, but just talk about angle bisectors as well. So we did good. All right, that's all I have for today. Hopefully this isn't a lesson that is over the top and too crazy to comprehend. I think it takes a lot of stuff that we've talked about with segments, and now it applies it to angles and angle measures. So hopefully a lot of it was familiar. If not, make sure you shoot me an email with a question, and